Hello everybody, I'm Francesco Silvestri, and in this brief announcement I will introduce a computational model for tensor core units, and this is a joint work with Rezaul Chowdhury and Flavio Vella. We all know that deep learning is nowadays used in several application domains, and that we need big data to obtain interesting results from the deep learning models. However, big data and deep learning has both performance and energy issues. How can we achieve at the same time high performance without increasing the energy requirements? The current approach, with the end of the Moore law, is to develop domain-specific hardware circuits for deep learning. However, now the question is, which computational part of deep learning should be targeted? That is, which part should be implemented as a hardware circuit? Well, the answer is simple. It is small and dense matrix multiplication, because this operation is a frequent primitive in machine learning and deep learning in particular. It has a high computational cost, but it can be easily implemented on a circuit. So you have now several hardware accelerators based on the hardware implementation of small and dense matrix multiplication. We call this family of accelerators with the name Tensor Core Units, or TCUs. Some important examples are the Google Tensor Processing Unit, the NVIDIA Tensor Core, or processors like the Intel Knights Landing or the Apple ARM A11. The two questions that we are willing to answer with our work is, first one, can we extend the application domain of TCUs? So TCUs have been introduced for deep learning, but can we use them for improving the performance of other algorithms from other application domains like high performance computing or data mining? And an example is given by graphical processing units, GPUs, that were introduced mainly for gaming, but now they are used in several application domains like machine learning itself or bioinformatics and high performance computing. The second question is, are TCU algorithms fully exploiting TCU accelerators? We would like to design efficient algorithms that exploit these accelerators, but we also like to know if these algorithms are optimal or not, if we can improve them or not. To answer these two questions, we first need to introduce a computational model for TCUs. And this model has to capture the three main features of tensor core units. The first one is high performance small and dense matrix multiplication. The second one is a latency cost, because we have to pay a fixed amount of time every time we need to set up the hardware. And finally, an asymmetric behavior. That is, in the hardware accelerators usually support a tall left matrix and a square right matrix. In the paper, we introduced the ML-TCU model, which is a variant of the RAM model characterized by two parameters M and L, which capture the size of the cost of the matrix multiplication supported by the hardware. This circuit for matrix multiplication can be exploited by the operation mult A, B, and R, where A and B are two matrices and R is a programmer-defined value, which can also depend on input size. So the left matrix A is a matrix of size R times square root of M, while B is a square matrix of size square root of M times square root of M. Note that the number of columns of A and the number of rows and columns of B are fixed and depends on the hardware parameter M. In the model, the multiplication between A and B takes R times square root of M plus L time. So we pay a latency cost L plus the cost of reading and writing the input matrices. Note that in this model, the cost of the matrix multiplication is negligible compared to the cost of reading and writing the input and the output. The overall running time of a TCU algorithm is defined as the total time including CPU operations and TCU operations. Now that we have a computational model for tensor core units, we can start designing efficient algorithms that exploit these hardware accelerators. As an appetizer, in this brief video, we'll see how to multiply two large square matrices that don't fit the TCU unit. Assuming that we have two matrices, dense matrices of size square root of n times square root of n. And now we'll see how to multiply these two matrices in time big O of n to the 3 half over square root of m plus n over m times L. So the idea is to split the left matrix A into vertical strips of size square root of n times square root of m, while we split matrix B into square matrices of size square root of m times square root of m. Then we might perform n over m matrix multiplication using the tensor coordinates, where we multiply a tall matrix from the left matrix A and a square matrix from the right matrix B. The large dense matrix multiplication was just an appetizer. If you want to see other efficient algorithms that exploit tensor core units, you can give a look to the extended version of this brief announcement available on archive at this number. In this paper, you'll see algorithms for several problems like dense and sparse matrix multiplication, FFT, stencil computation, the Gaussian elimination paradigm, then some problems on graphs like the graph transitive, closure, or all pair shortest distances, and then for linear algebra like integer multiplication and batch polynomial evaluation. To conclude this video, some open questions. So first one, which other computational problems can benefit from a tensor unit? For instance, can we sort with tensor core units? The second question is, so hardware accelerators have a parallel tensor and low numerical precision, and the current model don't capture these features. How can we extend the model in order to have parallel tensors and low numerical precision? Finally, does experimental performance on these hardware accelerators behave as predicted by our theoretical model, the ML-TCU model? I thank you for your attention, and I'm waiting your question in the Slack channel.